Okay, so today we're going to start trig identities. First of all, what is a trigonometric identity? It is a relationship between two or more trig functions expressed as an equation. Just to give you an example, let's recall the unit circle definition of sine theta. So the unit circle definition of sine theta is y over r. And let's consider, or let's recall, the unit circle definition of cosecant theta. If you remember, that's the reciprocal of sine, so that would be r over y. Okay, now I claim that that cosecant theta is actually equal to 1 over sine theta. That's my claim. Now, how could you prove that? So I want to show you how you prove such a thing. So the way to prove this thing right here is our first example of an identity. As you can see, it's an equation which expresses a relationship between the sine function and the cosecant function. Now, how do you prove it? Basically, what you have to do is you have to transform one side of the equation into the other, okay, using either facts that you already know or algebra, okay? And typically, so I could technically take the left-hand side and try to work it and transform it into the right-hand side, or I could do the reverse and I could take the right-hand side and try to transform it into the left-hand side. But generally speaking, you should pick the more complicated side and try to transform it into the simpler side. I'd say that looks more complicated, so I'm going to start there. So let's look at 1 over sine theta. So what is 1 over sine theta? The unit circle definition of sine theta, as we just saw, is y over r. So we have 1 over y over r. Now, this is like a complex fraction, right? I can keep this and then change this to multiplication and then flip this. So this is 1 times r over y. But of course, the 1 isn't doing anything here, so it's really just r over y. And if you recall, r over y is exactly the unit circle definition of cosecant theta. So as you can see, what I've done is I've transformed one side of this equation, namely 1 over sine theta, into the other side, namely cosecant theta, using established facts and algebra. So that's one of the ways that we can prove trigonometric identities, and it's an example of a trigonometric identity. Now, the point of this worksheet is you're really supposed to sort of determine the trig identities on your own, and the worksheet kind of guides you through it. Because it's meant to be done sort of in an exploratory fashion, I don't want to give you all the answers, but I do want to go over some of it, just so that you can have sort of a leg up. So first of all, the first type of identity that we're going to study are the so-called reciprocal identities. This very first identity here was an example of a reciprocal identity. As you can see, you're supposed to fill in the blank space here. Cosecant theta is the same thing as 1 over sine theta, okay? And the truth is that every trig function is the reciprocal of some other trig function. You can probably already guess. Secant theta, remember, that's the reciprocal of which trig function? It's actually the cosine function. Cotangent, if you think about it, I mean, for a very similar argument that we made here, you can conclude that cotangent is actually the reciprocal of tangent. So cotangent is 1 over tangent. And these next three identities are basically these guys, but sort of flipped upside down. Sine theta is the reciprocal of cosecant. Cosine theta is the reciprocal of secant. And tangent is the reciprocal of cotangent. So those are the so-called reciprocal identities. Now we're going to talk about some sine and cosine identities. So this sort of walks you through it. What is the unit circle definition of sine? Certainly that's y over r. What is the unit circle definition of cosine? That's x over r. What is the unit circle definition of tangent? Well, that's y over x. And it says use your answers to show that sine over cosine is equal to tangent. Well, we just have to sort of evaluate. So sine, as we saw, is y over r. Over what is cosine? Cosine is x over r. So the left-hand side of this equation is exactly this. Now I've got one fraction on top of another. I can keep it, change it, flip it. So that gives me this. And then what you'll notice is that the r's cancel, and you're left with y over x, which is exactly the unit circle definition of tangent. So this is a proof, this thing is equal to this thing, is equal to this, is equal to this. And so what we've done effectively is we've transformed this side of the equation into this side, and that's a proof that sine over cosine is tangent. A similar argument works for this problem here. You can do that one on your own. Let's jump to the next page. So we have the cofunction identities. What it asks you to do in this problem is to prove basically that sine theta is equal to cosine of 90 degrees minus theta. And we're going to use this right triangle to prove that that's true. So it begins by saying, write an expression involving theta for the measure of the angle in the top right corner. That's this angle right here. I'm going to call that thing x for convenience. Okay, so that's my angle x. Now, what I know is that these three angles add up to 180 degrees. So x plus theta plus this angle here, which is a 90 degree angle, has to be 180. And then what I can do is I can actually solve this equation for the angle x. If I subtract 90 and then subtract theta, I get 90, x is equal to 90 minus theta. So this angle right here is actually 90 minus theta. Okay, so the next question is, what is cosine of 90 minus theta in terms of A, B, and or C? Well, the cosine of 90 minus theta is this angle right here. So asking what is the cosine of this angle, well, the right triangle definition of cosine is adjacent over hypotenuse. The adjacent side of this thing is A, and the hypotenuse is C. So the answer is A over C. What is sine theta in terms of A, B, and or C? So theta is this angle right here, and so the sine of this angle here, remember the right triangle definition of sine is opposite over hypotenuse, so the opposite side is A, over the hypotenuse is C. Well, if you notice, these two expressions are exactly the same, which means that this is exactly the same as that, which is exactly what we wanted to prove. So that proves that sine theta is equal to cosine of 90 minus theta, and the next two problems here basically show you it's the same argument being made over and over again. The answers are basically, cotangent is going to be tangent of 90 minus theta, secant is going to be cosecant of 90 minus theta, cosecant is going to be secant of 90 minus theta. So this group of identities involving the 90 minus theta, those are the so-called cofunction identities. Basically because, in every such identity you have a function and its cofunction, right? Sine and cosine, cotangent and tangent, secant and cosecant, cosecant and secant, and so on. Okay, so moving on. The Pythagorean identities. These are the most... So the cofunction identities, I'll tell you, are sort of less important. They don't come up that much. The original identities we did, the reciprocal ones, and these Pythagorean identities are extremely important. So let's have a look at this diagram. It says explain, so refer to the unit circle, okay, to the right. So this thing is a unit circle. And it says explain why OP is equal to 1. This is point P, this is point O. So OP, that's this line segment right here. Well, that's a radius of the circle. And this is a unit circle, which means radius 1. So the answer is it's a radius. That's why it's 1. Okay, now why is sine theta squared plus cosine theta squared equal to 1? Well, look, the sine of theta, so here's this angle theta. The sine of theta is y over r, but because this is a unit circle, r is 1, and therefore sine of theta is in fact just the y coordinate of the intersection point, which we're calling y. And then we have cosine theta. What is cosine theta? Technically, it's x over r, but since r is 1, that's really just x. In other words, the x coordinate of this intersection point, which we're calling x. So cosine theta is just x, right? So the claim that we're trying to establish is really this, that y squared plus x squared is equal to 1. Can you see why that's true? Well, look, I mean, basically, the length of this segment right here, that is x. And then the length of this segment right here, that is y, the y coordinate of this point. And the length of this side right here is 1. And if this is a right triangle, if you use the Pythagorean theorem, you find this side squared plus this side squared equals 1 squared, which is exactly what this equation says. So the Pythagorean theorem tells you that this equation is true, y squared plus x squared equals 1, but y squared is just sine theta squared, and x squared is just cosine theta squared. This next thing I want to point out, so this identity here is our first Pythagorean identity. I want to point out sine theta quantity squared is typically written as sine squared theta. We usually put the 2 here. That might seem a bit strange. I just want to be clear about this. If you see this expression, sine squared theta, there's sort of 2 ways that you could conceivably interpret it. One is you could interpret it as this, sine theta squared, like you take the sine of theta and then square the result. That's what it in fact means. You could also say, oh, maybe it means this. Maybe it means sine of theta squared. It does not mean that, okay? In fact, these are 2 totally different things. This kind of expression very rarely comes up. So, yeah, just bear in mind, sine squared theta means this, sine of theta quantity squared, not sine of theta squared. Now, to derive the remaining 2 Pythagorean identities, we use division. So let's begin with the original Pythagorean identity, okay, which we just derived. And the instructions are divide each term by the first term, right? Or divide everything by sine squared theta. So if I take this equation and I divide both sides of the equation by sine squared, in other words, I divide everything by sine squared, this is what I get. Well, that actually can be simplified because sine squared theta over itself is, of course, just 1. Plus, now cosine over sine, you might remember from an earlier page, cosine over sine is in fact cotangent. But of course, this is cosine squared over sine squared, so this is actually cotangent squared theta. Equals 1 over sine squared theta. Again, you might remember reciprocal identity. 1 over sine is in fact cosecant. Well, this is 1 over sine squared, so this is actually cosecant squared. That's the second Pythagorean identity. And then in the last bit, you'll obtain the last Pythagorean identity by dividing everything by cosine squared. You can take care of that on your own.
I have a quick notation question.
Yeah, sure.
For gradient here, when it's a vertical vector, and assuming first is x, the bottom is
Yeah, correct. Yeah.
Okay.
Okay, so identities with negatives. So we've done stuff like this before. I think this page is pretty straightforward. It says basically sketch a negative theta angle in the circle. So here's theta. Negative theta would look like this, okay? And basically, what you'll sort of notice is if you think about the coordinates of this point, the x-coordinate is going to be the same, but the y-coordinate is going to be the opposite of the y-coordinate up here. That tells you that well, let's think about it. What's the sine of theta? It's the y-coordinate of this intersection point. It's just y. But sine of negative theta is the y-coordinate of this intersection point, which is negative y, okay? So what's the relationship between sine theta and sine negative theta? The answer is they're opposites, right? These 2 expressions are not equal, but they're opposites. So we conclude that the sine of negative theta is actually the opposite of sine theta, right? Okay. Very similarly, another argument like that can be made here. I'll let you figure it out on your own. And then I think that's all that I want to say. So, as I say, this worksheet was meant to be sort of very exploratory. You figure it out on your own, and that's why I'm not meticulously going through all the problems and explaining things directly. I do kind of want you to struggle through this one and figure these things out for yourself. In the next video, I will summarize the results of all of these investigations. I'll summarize all the trig identities that we derived from this, and then we'll start to really get into the business of proving new trig identities, okay? Which is what the unit is really about. This was just kind of an introduction. Okay.